Bismillahirrahmanirrahim. Today, what we are going to study a very small topic from chapter 6, that is banding shear or the transverse shear. We have just seen in the last chapter and the chapter 4 that there is always a there is always a shearing force V whenever we have some transverse load applied on the beam, right? So we did not consider that V very much in that section, but now we are going to see a little bit in more details in this chapter 6. It's a very small topic. Obviously, we will go for a for a just to give you an overview what the shear force is and how it is applied and what's its effects, why we use it, and by the end of the day where we use it. So chapter 6, a very small portion of the theoretical portion of the chapter 6 we'll be going to cover in this section, and we will finish it by today with some with one numerical probably, and then we'll give you the assignment about this section, right? So let's share the screen. This is the transverse or the banding shear. That is a smaller part of the chapter 6, right? Fine. Okay. So what we have studied till now, right? We have the stresses. Stresses are the basically internal reaction of the material against an external load, that is internal resistance of the material, that is against the load that is being applied on the component or the shaft or the beam, right? There are mainly two types of the stresses. One is the normal stress and another one is the shear stress, normal stress, and the shear stress. Further, this is the axial stress, right, and the normal bending. This is chapter 2, and this is chapter 5, right? Then, when we come to the category of the shear stress, we have direct shear, that is again chapter 2. Then torsional stress, that is chapter 4, right? And then in chapter 6 we are going to start today, that is chapter 6, that deals with the bending shear or the transverse shear. Means this is the shear force that is purely being generated into the component because of the transverse load when that is being applied, right? So whenever there will be some bending, whenever there will be some bending, there will be definitely a shear stress will be there. This is what we have already seen, that if we have a beam like this and we applied a transverse load, again the chapter 5 and the 4 as well, and if we take the section over here, right, and we draw this free body diagram from here to here, right, so we will see that there is always a positive convention for the bending as well as for the shear stress. This is V and this is moment, right? And likewise, if we draw this section, so this section will be like this one. So bending will be like, moment will be like this one, and shear will be like this one. So this is moment. This is what we have already seen. Today we will explicitly discuss with this V, right? So what we have done till now? What we have done till now is that in chapter 2, we have seen that whenever you have some axial loading, that may be a tensile load or a compressive load, so sigma is always there, right? Sigma is the normal stress against, and then you have the epsilon, that is the normal strain over there. And if we take the section of any particular thing, that is this one, if this is a cross section like this one, right? So this is the section, right? And if a load P is applied into this direction, if I draw this into this format, so a P load is applied into this one, and this is the side view of this, right? So this is the tensile force that is being applied. So sigma will be there. So and sigma will be P over A, and this will be the average normal stress that will be distributed all along the cross-sectional area. It will be uniformly distributed along the cross-sectional area of the beam, right? Likewise, we discuss this direct shear stress over there as well. That was tau, right? And tau was there, and tau again in that particular section was P over A. So both sigma was P over A and tau was P over A. Both were the force per unit area or the load per unit area, and both were uniformly distributed on the cross sectional area, and that's why we always take the average of that particular one. But in this chapter we are going to change this concept a little bit. We are going to discuss a little bit more detail what this shear stress is. It will no more be evenly distributed on the cross section like we just discussed into this part of the cross section, right? Another part of the shear is coming from the torsional one, right? And in torsion we know that whenever we have some rod and a torque is being applied on it, so torsion will be there, right? And torsion again was we distribute we say it with a T. That was we will discuss in next slide as well. So torsion, and then there will be some shear stress as well, right? So in both cases of these direct as well as the torsional one that we deal in chapter 2 and chapter 4, we are keep on discussing the shear stresses. But the chapter 4, the shear stresses are just because of the torsional motion or the twisting motion of the shaft, right? And in this particular chapter 6, bending stress, where we are going to discuss, this will be purely because there will be a transverse load. There will be some transverse load like this one. And whenever there will be some bending because of this moment M, so there will always be some shear force. And today we are going to discuss this shear force, right? So column tension, the sigma is because sigma is force per unit area. This is what we have discussed, right? And then this is Hooke's law, how we define this. Then we discuss the bending. This was in chapter 3, right? No, not in chapter 3. This was in chapter 4. Chapter 3 was torsion, right? Whenever we have bending, this is the positive bending because it is a smiley face. So this is positive bending, right? Whenever you apply a moment about the z-axis into this direction. And if it goes like this one, sad face, so this will be the negative one, right? This is the convention. This is the positive. This is the positive bending, and this is the negative bending. Likewise, we know whenever there is bending, there is always a shear stress as well. We discuss in chapter 4, and we are going to discuss it today as well, right? And pure bending was in our case, that was sigma max was m was equals to mc over I. It was initially it was rho, but then we converted with the mc over I when it is maximum over there. So sigma max was in that particular case, sorry, in this particular case, sigma max, what we have studied, it is m minus my over I, but we studied m minus mc over I, and c was the maximum distance from the neutral axis, that is this one, from the neutral axis. This was C. And whenever the y distance or the rho distance is maximum, so sigma will be maximum in that particular case, right? And from there, if you remember, we discussed the strain as well. That was my over ei or mc over ei, right? And obviously whenever the bending is there, so both compressive stresses are there, and the tensile stress is there. Whenever you will get this sort of bending, that is a positive bending, this surface will be under compression and this surface will be in tension. But at this surface and at this surface, these normal stresses sigmas will be maximum. So that's why if we draw the distribution of the stresses, so these are the negative one, these are the positive ones. So these are the tensile one, and these are the compressive distribution of the stresses in this particular case. This is what we have already discussed. This is the compression phase and this is the tension phase for this positive bending. It will be opposite agar if it is the negative one. So that was the shear stress, direct shear stress. If you remember that if we have the if we have this sort of the case, the shear stress will be into this region. Since this will be the parallel to the plane, so you have the shear stresses, and you can we have discussed in detail in chapter 2 for this one, right? And then we discuss in chapter 3, we discuss torsion, and torsion was T rho over J, and then we discuss the theta TL over, this was TL over Gj, and this was the theta. Theta was the angular deformation against some particular torsional loads. So this theta was the deformation, and shear stress because of the torque, that was T rho over J, right? And Tc over J was the tau max. Whenever it will be maximum, so it will be tau max will be Tc over J when rho will be equal to the radius of that particular shaft. So it will be maximum on the outer surface and it will be zero in the center of that particular shaft. So that this is what we have already discussed in detail in chapter 3. So now what we are going to discuss. This is the extension of chapter 4. That was the pure bending, right? So whenever we have at some transverse load P like this one, right? And we cut the section over here, and then we can see that this is the section which will be the sum of the moment and the shear force. Moment is M and shear force is V. This is what we have discussed in chapter 4 and in chapter 5 in detail. So the net effect of this transverse load will be this bending stress plus transverse shear stress or the bending shear stresses. So we have to deal with it differently. And whenever we want to calculate the total shear stress or the total stress into a particular body, so then we will have to calculate this transverse shear, that will be the tau separately, and the bending stress that will be calculated separately, that will be the sigma. That is what we have discussed in detail in chapter 4, right? So the net, whenever there will be some transverse load, so moment will be there, resultingly bending will also be there, as well as shear stress will always be there. And then we have to taken care of these shear as well as the transverse shear as well as the bending shear for that. And the expression for this, we are not going into the proof of this expression. We are just looking at the expression, and we are dealing with when we are discussing what are the key parameters for this transverse shear. So VQ over IT is the expression to calculate the bending or the transverse shear. It is no more now, tau is no more now P over A that was uniformly distributed into the whole cross section of that area. Now we will have to see that how this tau XY, that is because of the normal loading, transverse loading, sorry, not the normal loading, transverse loading of the beam. So what is it? So V, that is the normal force that will be given to you. That will be the not the normal force, that will be the shear force that will be given to you. Then I is as usual, that is the second moment of area or the area moment of inertia. That is, we know how to calculate that. We are now you should be master in calculating the I, because we are calculating the I in chapter 3, in chapter 4, in chapter 5. We are keep on calculating the I. T is basically the width of the section. This is the T. This is not the B. In fact, this is T, right? And what is Q? Q is the first moment of area that gives me the information of the centroid, right? And how we calculate it? We calculate, this is the expression for the Q. And how we calculate is, we calculate by doing all the integration over the area A dash. This is the area A dash over here. So A dash and the Y dash. What is A dash? A dash is the cross-sectional area above the point of interest. What is the point of interest? Now this is the neutral axis, and it can be anywhere above and below the neutral axis. For example, in this particular case, this is the P point. that is the area of interest across a point of interest, not the area. So the area will be a dash. This a dash will be the area of this section above the point P, above the point. So this will be the area for this a dash. So this may be vary. For example, if this is like this one, this is neutral axis, and this is A, this is the point of interest P. So this whole will be your area, whatsoever that is. Right? So point of interest can be anywhere above the neutral axis, on the neutral axis, below the neutral axis, or the extremes of the section. Right? So, so the area above or below the point of interest, that will be the A dash. Right? And Y dash will be, what will be the Y dash? Y dash is the distance of the centroid of the area. That is the centroid of that area, because it is a, it will be a, it may be a rectangle, it may be a square, and it will be exactly in the center. Right? So it will be the distance from neutral axis, the centroid of that area A dash from the neutral axis. This will be Y dash. Right? So now we dissect this. What happens? Now the whole dynamics or the whole distribution of transverse or the bending shear depends upon the Q, where your point of interest is. Right? Obviously, it is dependent on the A and the Y. When Y will be maximum, and where the Y will be maximum, if our point of interest exists on this neutral axis. Right? If a point of interest exists on the neutral axis, so the above area will be maximum. Agreed? So when this area will be maximum, Q will be maximum, so tau xy will be maximum. And when Q will be minimum, when area will be minimum. And when the area will be minimum, it will be minimum when the point of interest exists at the topmost position, like this one. For example, I must change the color. Right? So this, if this is the area of our interest, so it will be minimum. If this is our area of interest, it will be maximum, because in this case, area of whole this will be maximum, and in this particular case there will be no area above this point, so it will be zero. When it will be zero, so Q will be zero, resultingly tau x will be zero. So what we conclude over here? We conclude that Q is zero at the top and the bottom of the beam, at the top and the bottom of the beam. So resultingly tau will be zero. Q is maximum at the neutral axis. Q is maximum at the neutral axis. So resultingly tau is maximum over the neutral axis. Right? So you need to calculate how to calculate Q. You are done. Because V will be known, width, this width will be given to you, width of the section, that is T, and I is the second moment of area or area moment of inertia. So you have you must be master in calculating all this stuff. So you will V will be given to you, so you will put these four values and you will calculate the tau xy into that particular one. Right? So where we use it? What is the application of this? Right? For example, this is your beam. This beam is made up of different segments of the different layers of the material. For example, there are 4 layers of the timber or 4 layers of the wood, small strips of the wood, and you glue it, or you don't glue it, you put it all together, and then you apply the load. If they are not glued, what will happen? It will be like this one, they will be displaced. And to keep them joined, we put the nail or we glue them. Right? So what happens when you glue them? These all faces, these are the different faces which are, right? These are all faces, and these faces slides against each other. So because of this load, because of the load P that is being applied, one will be the, if I take this section, and if you remember that if we have this sort of beam and we apply P load over there, and I take this section, so it will be positive m and it will be negative v. And if I take the cross section of this, right, this is the cross section, so it will be like going this one and like going this one. This shear, this is v. This shear, which is the positive shear, as per chapter 2, as per chapter 4 and 5, this is positive shear because this face is going up, this face is going down. When the top faces slide against each other, there is always a shear stress, right? Likewise, they are equal and opposite. Right? So this is what we have already done in chapter 2 as well. This is the sigmas and this is the tau xy's and tau y-axis, right? And right, so now just see, if I take this top section, top layer and the bottom layer, will there any be this sort of force? There will be some force into this one, but there will be no force because there is no joining surfaces on this and on this. When there is not this one and not this, so there will be no tau on this part as well, because when this is tau y-axis 0, tau y-axis 0, tau xy will be 0 as well, because the all forces to keep the equilibrium, this should be equal to this and this should be equals to this should be equal to this and opposite, this should be equal to opposite this one. When this is 0, right, when tau y-axis is equal to 0, so we know tau y-axis equals to tau xy, so tau xy will be equal to, this is chapter 2, tau xy is tau yx equals to tau xy, and if this is equals to 0, so tau xy equals to 0, right? So physically there will be no constraint, there will be no constraint on there will be no shear stress onto this one, right? This is what the 3D view of this one. That's why on the top surface and on the bottom surface, tau bending shear or the transverse shear is always 0, right? And we have seen the distributed, it is no more average, it is no more equally distributed on the face, but it is always maximum at the neutral axis and 0 at the top and the bottom faces of that, because there is on the top and the bottom there is no face which will slide against each other, resultingly no sliding motion, no shear stress, resultingly no bending shear will be there, right? So it is always maximum, and this is just one expression for that, for the different, for different shapes like this one, this is the rectangle shape, this is for the circular shape. We will not go into the detail from where this is called, this is coming. So these are basically the distribution of the tau. If you look at this, when this y1 is c, when y1 equals to c, so c square will be over c square will be 0. It will be 0 when y1 equals to c, and 1, and when this is, sorry, not 0, it will be 1, sorry. So when y1, this y1 will be equals to, this y1 becomes equals to c, y1 equals to c, so c1, c square over c square will be 1, 1 minus 1 will be 0, resultingly tau will be 0. So at this surface tau will be equals to 0. And when y1 will be equals on the neutral axis, so y1 will be 0, so 0 over c will be 0, and 1 minus 0 will be 1, so tau will be 3v over 2a. At this, tau will be 3v over 2a. That will be obviously maximum. And between this, the distribution will be. So we will see in machine design that it will be like parabolic distribution, because the dependency is on the scale, right? So it will not be a straight line, it will be a parabola like this one. So this is how the distribution maximum over here, and ultimately 0 will be on this face and the on this face, right? Now, so here we are going to comprehend our 4 5 chapters which you have seen. Axial sigma is f over a, even tau is f over a or p over a, whatsoever that is. The f is the load or the p is the load, right? For bending, sigma is equal to mc over I. In pure bending, there will be sigma. Bending and shear, right? If you have transverse loading like this one, sigma will be mc over I, as it is this one, and tau average will be vq over it. Whereas tau in this particular case, torsion, it will be t rho over j, but we have studied, and when rho will be maximum, that will be equal to the radius of the rod, so it will be maximum. So tau max will be t r over j, or the tc over j, whatsoever you want to say. So if we conclude it, so this will be uniformly distributed, uniformly distributed against the cross section, pure bending and pure torsion. This will be maximum at outer surface, maximum at outer surface, and this will be maximum at neutral axis, and 0 at the and 0 at outermost surface. This is what we have already seen, right? So this is all. This is all about the stresses. Now we have discussed these 5 types of the stresses in detail. In chapter 7 and in chapter 8, we will see how to utilize all these uh, forms of the shears, and then we will converge to the transformations, and then we will converge to ultimately to the Mohr circle that will conclude our whole syllabus into this section, right? So here we are going to solve the problem 6.1. So this is basically, we will quickly go through. There is nothing more than it. I is given to you. What you have to calculate, you just need to calculate the shear force, right? V, that is V, right? These are the different sort of loadings. Now we know that sum of all the forces about y-axis will be equals to 0, and if this is 1.5 kilonewton, if I take the section over here and I draw the free body diagram, it is 1.5 going into the positive y direction. This V is going to the negative y direction. Statically, I am talking. M is positive, right? So when we will sum of all the forces about y-axis, Fy equal to 0, right? So finally, V will be equals to 1.5 kilonewton, right? So this is a same is case with over here. If we take this section as well. So B, A is 1.5 kilonewton, B is 1.5 kilonewton, and we will utilize this V. Now, where is the trick? Trick is over finding the I is given to you. You must know how to calculate the I in detail for this I beam or the T beam or the uniform cross sectional area like rectangle or the square. You must have a very clear understanding how to calculate I if you don't, if I is not given to you, right? This is what we have already done practice in the chapter 4 and chapter 5 as well. So Q is A Y1. What you want to say? This is what we have already seen. That's A this because this is joint A, this is joint B. Tau XY bending shear or the shear or the transverse shear is always happen to be on on the joining faces, right? So these are the two joining faces, joint A and joint B. So tau xy will be over there, number one. So what we want to calculate? We want to calculate this tau average or the tau at joint A and joint B. So we want to calculate Q. This is the whole distribution, dimensions of this one, right? So first is this section of interest. This is a point of interest where the joint A is there, right? Okay, fine. Let me discuss it again. So what is our point of interest? Our point of interest is this, right? And our point of interest is this. This is a point of interest, right? So what we want to calculate? We want to calculate Q. Q is the area multiplied by the centroidal distance. Centroid will always exist in the center of the. This is now area which we want to calculate. A dash. This is our A dash, and this is the center point, which is the centroidal distance y dash. So if I take joint A, y1 will be 0.0417 meter from the neutral axis. This is the neutral axis. We have clearly mentioned that this distance y dash will be from the neutral axis. So neutral axis exists at C. If this is 68.3 millimeter, total is 120. 120 minus 68 will be this distance. Total this distance, sorry. This distance from this point to this point. And then since it is 10, the center of this, sorry, it is 20, center of this will be at 10. So this point will be at 41.7 millimeter or 0.0417 in meter. And area will be 0.1 into 0.02, that will be the area. So area into centroidal distance, so you will get this 83. Likewise, for the lower one, it will be area will be this multiplied by this multiplied by further multiplied by this. So this is your Q dash. And then you put the value of T. T is basically the this width. This is this width. This is 20, right? So so V is given to you. We have already calculated 1.5 kilonewton, that or the 1500 Newton. This is basically Q. This is Q. This is V. This is I given to you, and this is T, and then you will calculate T average, tau average over there. Likewise, you can calculate the tau average over there, right? So this is how you can calculate. This is very simple one. Only trick can be there when you have different sections. So you need to calculate I. How to calculate I? This must be very clear to you. How to calculate Q? You must be very clear to it. A rest is statistics, right? Statics, sorry, not the statistics. That rest is the statics, and in statics you need to calculate sum of all the forces equal to 0 and sum of all the moments should be equal to 0, and then you can go for the shear forces V, and you can calculate accordingly for the stuff for this one, right? So what you need, just you need to calculate V, and V is very easy to calculate. You take the section, you subtract statically all the forces, and you are done with the V. You put the value of V into the formula. You must have an idea how to calculate Q. You must have an idea how to calculate I, and these are very easier. I don't think there is any complication exist. And then you will put the value of T, and then you will end it up. And then obviously there may be some manipulation of all this. So I'll give you an assignment on this, and you will do that, and hopefully you will master all this. Thank you so very much, and hope to see you in next lecture, where we will start chapter 7, and then we are going towards the conclusion of this whole syllabus, right? Thank you very much.